Okay, welcome everyone. Today's session is going to be particularly exciting because we're diving into the foundations of what makes your computers and phones work. That's the operating systems. So distributed systems are essentially basically multiple computers working together, and to make them work together effectively, we need to understand how each computer operates individually. So today we're going to explore how multiple apps like maybe Spotify and WhatsApp can simultaneously run on our phones without crashing into each other. So also just to be mindful, today's session is just a brush through of a few basic concepts that are a prerequisite to the course CS 6650 Scalable Distributed Systems. I will be going through some important topics while correlating it with relatable or real world examples so that you can understand it better. So let's move on to what is an operating system. So think of an operating system as the conductor of an orchestra. Just as a conductor ensures that all the musicians play in harmony, the operating system ensures that all parts of your computer work together seamlessly. So let me break it down into its three main responsibilities. The first one is hiding hardware complexity. So what I mean by that is imagine if Instagram developers had to write code to understand every single camera model in every single phone. That sounds impossible, right? So that's where the OS comes in. It hides all that hardware complexity. Instagram just needs to say, take a photo, and the OS handles all the complicated camera operations. And the second main responsibility of an operating system is resource management. So OS acts like a traffic controller at a busy intersection. So let's say when multiple apps want to use your phone's processor or memory, the OS decides who goes first, for how long, and when to switch, and all of this happens in milliseconds. And the third and the most fascinating responsibility of an operating system is isolation and protection. The OS basically acts like a security guard. When you're running Chrome and Spotify together, the OS ensures that they can't interfere with each other. And it's basically like having separate secure rooms for each app, and even though all of these rooms exist in the same building. Okay, let's move on to the core components of an operating system. So there are three core components of an operating system. The first one being a file system, and the second one is the scheduler, and the third one is the device driver. We'll talk about the file system. Imagine walking into a library where books are scattered randomly. It would be chaotic, right? The file system is like a librarian who keeps everything organized. So let's say you have to save a photo. The file system knows exactly where to put it and how to find it later. And imagine you save a photo somewhere and you're not able to find it later. I think the operating system solves that issue. And next we have the scheduler. Think of the scheduler as maybe the world's most efficient program manager. Let's say you're running 10 apps at once. The scheduler decides which app gets the processor and for how long, and is making thousands of these decisions in every second. In distributed systems, this becomes even more interesting because we're scheduling tasks across multiple computers. And lastly, we have the device drivers. These act like universal translators. Let's say you have a printer and the printer speaks a particular printer language, and you have a mouse that speaks a mouse language, and your keyboard speaks a keyboard language. What the device driver does is it translates between these devices and the operating system. So without a device driver, it would be like having a conversation where everyone speaks a different language. That's why device drivers are essential to an operating system. Now, let's talk about something that's really exciting, processes. When you click on the Spotify icon, what actually happens? The program transforms from just one something that exists on your hard drive into a fully living, breathing process. It's it's like the difference between maybe a recipe in a cookbook and actually cooking the meal. So every process has 5 essential parts, and the first one is the program counter. The program counter is basically a bookmark. It's like a bookmark in a recipe book, and it shows you exactly which instruction you're executing right now. And the second one is the stack. The stack is basically a short-term memory. It handles temporary data and function calls. Imagine solving a math problem, and every time you're solving a math problem, you have a rough column where you work out things that you jot down, intermediate results. So that's basically what the stack is. And the heap, that is the third one. The heap is like an expandable garage storage. It can grow or shrink based on what the process needs. And if it needs more space, the heap can provide it dynamically. And the fourth part of process is the text section. This one contains the actual program code. It's like having a complete recipe book. And the last part is the data segment. The data segment holds global variables. Think of it as a pantry where you can keep ingredients and you'll need that you'll need throughout the cooking process. Moving on to process states. This slide, I'm going to make it super relatable with a coffee shop analogy. Okay, imagine you're getting coffee at Starbucks. So, what is the first thing that you would do? The first thing that you would probably do is to walk in. That, in this context, is the start state. The process is being created just like you're entering the shop. That is the start state. The next thing that you would probably do is stand in line. That, in this context, is your ready state. You're ready to order, but waiting for your turn, just like a process waiting for its turn on the CPU. Okay. The third step is when you're waiting for your coffee after. Okay, the third step is actually ordering. That's the running state. We're actively being served, just like a process is actively using the CPU. Okay, that's the third state. The first one was start, second is ready, and the third is running. Now you're waiting for your coffee that you ordered. That is the waiting state. The process might be waiting for data from the hard drive, just like you're waiting for your drink. And finally, when you leave with your coffee, that's the terminated state. The process has completed its job. When we talk about distributed systems in this context of process states, it becomes interesting because processes on different machines need to coordinate their states. If I were to explain that in the context of the same coffee shop analogy, it's like if Starbucks had multiple branches and all of those branches were working together just to serve you your coffee. So that's about process states. Let me repeat it again. The first one is start, then ready, then running, then waiting, and the last is terminated. So now let's talk about the process control block or the PCB. And this is one of the most ingenious concepts in operating system. Think of it as a digital ID card that contains everything that the OS needs to know about a process. So let me break it down to you with a real world example. When you go to the airport, your passport contains all crucial information about you. It might be um, your ID number or your photo, country of origin, whatever. Similarly, a PCB contains firstly a process ID or the PID. That's basically like your passport number. And the secondly, it contains a process state. That's what we discussed previously in the previous slide. That's your running, waiting, terminating, etc. And the third one is the CPU scheduling information. That's like your flight priority status. And third and fourth, for fourth one, we have memory management information. That's basically that the resources that the process is using. And then we have input output status. So input output status is defines what files or devices that the process is currently accessing. So this becomes especially crucial in distributed systems because we need to track processes across multiple machines. So we need to know, we need to have information about each process, and that is given to us with this process control block or the PCB. It's basically like having an international passport that works across all countries. Okay, moving on to threads and concurrency. So, according to me, this is one of the most powerful and foundational concepts in modern computing. And it's also one of the most important operating systems concepts that you will be using in this course. Towards the end, you will be using multi-threading. So let me again use a real-world example to explain this concept. Think of a process, the one that we discussed in the previous two slides. Think of it as a restaurant. So within this restaurant, there are multiple workers. They might be the chefs or the servers or the management, and all of them are threads. So inside a process, we can have multiple threads. They share common resources like in this context, like the kitchen, ingredients, and tools, but all of them operate independently to ensure that the restaurant runs efficiently. So let me explain this again because this is important. A process in this context is a restaurant, and the threads are the workers, like the chefs, servers, and the cleaners. And what do they do is that they work or operate independently, but they use common resources so that the process runs efficiently. So now threads enable applications to perform multiple tasks simultaneously or almost simultaneously. For example, imagine a web browser like Chrome or Safari. You can download a file while scrolling through a web page and also watching a video all at the same time. It's what is happening in the background of all these tasks are being handled by a separate thread, working concurrently to enhance your user experience. So now every time you're doing all of this on a web browser, just think of threads. Moving on, we have, let's talk about the two main types of threads. The first one is a user level thread, and the second one is the kernel level thread. So whatever might be a positive aspect in user level threads is like a negative aspect in the kernel level threads. So let's dive into user level threads. Here, these threads basically operate entirely in the user space and they don't involve the operating system's kernel. So let's again maybe revisit the restaurant analogy where user level threads are like the workers managing themselves without a manager's supervision. And this anatomy allows them to work faster and adapt more flexibly to changes. Context switching between these threads is fast because there is no need to involve the operating system. So let me just briefly explain what context switching is. Context switching is when the state of one thread is saved and the state of another thread is probably restarted. So this happens fast in user level threads because there is no need to involve the operating system because they're working entirely in the user space. However, there is a downside to user level threads. That is, if one worker encounters an issue, like running out of ingredients, then all the other workers are forced to stop working. Similarly, they also struggle with blocking system calls, where a single thread's blockage can basically halt the entire process. Now, coming to the next one, that's the kernel level threads. Here, the kernel level threads are managed by the operating system. In our restaurant analogy, this is like having a restaurant manager who oversees all the operations. So the manager can reassign tasks if one worker is delayed, ensuring smooth and independent workflow. Kernel level threads also enable true parallelism, allowing threads to run simultaneously across multiple cores in a multi-core processor. Because of this, they are very efficient. However, this efficiency also comes with a cost. The coordination and oversight provided by, in this analogy, the manager introduces an overhead. Because the kernel is involved, it introduces an overhead. And context switching between kernel level threads involves transitions into kernel mode, which is more resource intensive compared to the previous one, that is the user level threads. So when we talk about distributed systems, in this context of user level threads and kernel level threads, threads play a very critical role because imagine you're not just managing one restaurant, but coordinating operations across multiple branches. This requires precise synchronization and efficient task allocation across threads running on different machines. This is about threads. Next, let's talk about memory management. This is a fundamental responsibility of an operating system. Think of memory as a shared workspace where all the processes collaborate. Without proper management, it would be chaotic. The operating system ensures every process gets the memory that it needs while preventing overlap. So there are three key concepts that are needed for memory management by an operating system. The first one is segmentation and paging, and the second one is virtual memory, and the third one is memory protection. So coming to the first one, that's segmentation and paging. So in this case, imagine your computer, your computer's memory is maybe a city, and all the processes are its buildings. So segmentation is like dividing this city into districts. And paging is splitting those districts into uniform blocks. How does this help? It helps by managing operating system memory efficiently, and it also handles fragmentation. Moving on to the second one, that is the virtual memory. Have you ever noticed how your computer runs more apps than its physical RAM allows. If you've noticed this, that's basically the virtual memory in action. It tricks processes into thinking that they have more memory by using disk space when needed. It's it's essentially just like borrowing your neighbor's parking space when your lot is full. That's what virtual memory is all about. And coming to the last one, that's memory protection. Processes must stay in their lanes, and memory protection ensures that one process doesn't accidentally overwrite another's data. Just like guardrails that keep cars on the road. And this particular uh, memory management uh, method, that's memory protection, is vital for system stability and security. Otherwise, all the processes can override the other's data, and uh, there's a loss of data. Moving on to the next slide, we'll talk about inter-process communication, or IPC. Um, to better understand this, it's basically like if in a restaurant we had multiple chefs working in a restaurant's kitchen, then to create a perfect meal, they need to communicate effectively. So that is what inter-process communication is all about. Communication between processes so that they work effectively. So the first inter-process communication method is the shared memory. It's like a common chalk book where all the chefs jot down their tasks, and processes share a portion of memory to exchange data. This is very fast, but it requires synchronization to avoid conflicts. The second method is message passing. Think of this process as basically chefs passing handwritten notes. Processes send messages to each other, often using mailboxes or queues. Even though this method is slower than shared memory, it's safer as processes don't directly access each other's space. So if you want something safer, you go for message passing, but if you want something faster, then it's shared memory. And the last one is pipes and sockets. Pipes are basically conveyor belts transferring food between chefs, and sockets enable communication over networks, like chatting between distributed servers. And talking about distributed server systems, inter-process communication is critical for coordinating tasks across machines because of the possibility of having multiple machines. Coming to the next slide, this is input-output management. Input-output management in the operating system is a way of handling interactions with external devices like keyboards, monitors, and hard drives. And think of it as a translator between your computer and its peripherals. So there are three key concepts that we'll be discussing about input-output management. The first one is buffering, the second one is pooling, and the third one is interrupts. Coming to the first one, that's buffering. Imagine waiting tables at a restaurant. A buffer is basically like a tray that holds temporary food until it's delivered. So buffers basically smooth out the speed mismatch between fast CPUs and slower input-output devices. I'm pretty sure you would have experienced this while watching a YouTube video. And coming to the second one is spooling. Have you ever printed multiple documents? The OS queues them up in a spool, ensuring that the printer processes them one at a time so that they don't override each other and probably print everything on one paper. It's like an assembly line for input-output tasks. That's what spooling is about. Coming to the last one, that is interrupts. Interrupts are signals from devices to the CPU. It's like someone trying to get attention, like a waiter waving at a chef to get his attention. They ensure that the CPU responds promptly to urgent input-output requests while continuing other tasks. So these are the three topics: buffering, spooling, and interrupts in input-output management. Coming to the next topic, that is deadlocks and resource allocation. So how does a deadlock occur? Deadlock basically occurs when processes get stuck. It's like waiting for resources that are locked by other processes. A real world example to this would be maybe 4 cars at an intersection, each waiting for the other one to move, but no one's progressing. There are 4 conditions that we'll be discussing today that lead to deadlocks. The first one is mutual exclusion. The second one is hold and wait. And the third one is no preemption. And the last one is circular wait. So how does mutual exclusion work is when one process can use a resource at a time. So only one process is being allowed to use one resource. And the next one is hold and wait. I think this is one of the most common. This happens when processes hold resources while waiting for others. So they're not only not letting other processes use these resources that they're holding, but they're also waiting for another process that's being held by another process. So this becomes ends up in a deadlock situation. And third one, no preemption. This is when you can't forcibly take back resources from processes. And the last one, circular wait. It's when a chain of processes holds and waits in a circle. To handle deadlocks, what the OS can do is basically avoid them. That the best approach is to avoid deadlocks. That is by ensuring, how resource allocation doesn't lead to circular wait. But in case there is a deadlock, then you need to detect and recover. Detection is by how you perform detection is basically by monitoring resources, and recovering is by terminating or rolling back processes if needed. And deadlocks and resource allocation, talking about this in context to distributed systems, that deadlock management gets more complex because it spans across multiple machines. So handling all of this with multiple machines is complicated. Moving on to the last slide, that is security and protection. So security and protection is like the operating system's role. It basically is like an ultimate bouncer. It ensures that no unauthorized party accesses resources or data. Some of the key techniques that any operating system includes for security and protection are, maybe the first one is authentication. Authentication is verifying who's accessing the system. Think of it as showing an ID to the bouncer. And the second one is access control. This is defining who is allowed to do what. Just like a VIP pass allows access to specific areas, access control restricts user action. Students usually get confused between authentication and access control, but they're two different things. And another way technique that is used by operating system is encryption. Here, what is essentially done is data is scrambled to protect it, and it's like writing message in code. When we talk about distributed systems again in this context, we can take it even more further with network like level security measures like firewalls, VPNs, and intrusion detection systems. So, to uh, to wrap up operating systems, we can say that modern computing cannot exist without operating systems, and from managing processes, memory, to enabling communication and also ensuring security at the same time, OS makes everything possible. Okay. For those of you who are interested in distributed systems, it's the understanding operating systems, the fundamentals of operating systems is non-negotiable. And these principles that we spoke about today in class uh, can scale from single machines to massive server clusters working together. And next time, next time you multitask on your phone or run a complex app on your computer, just remember the magic that's happening behind the screens. Let me just stop recording.